afternoon to all of you on behalf of the president of the physics class of the Hungarian Academy of Sciences, who is on vacation. I welcome you. Today's open meeting has only one point in the agenda, namely the inauguration lecture of Professor Johann Rafelski, who has been elected as honorary member of our academy on May the 3rd this year. Probably it's a historical event not only by a Polish-born American professor gives an inauguration speech, but because probably the shortest time between election and the inauguration lecture is going to happen today. Professor Rafelski was born in Krakow, Poland, studied at high school and university in Germany, worked in Germany, France, South Africa, and now he is a professor in the United States in Arizona. He had long connection with our foreign member, László Csernai, with Tamás Bíró, who is in charge of one of our national projects. And probably these connections came to a conclusion that he decided to join one of our national programs, which is on nanofusion. He's probably one of the best known, not probably, certainly, one of the best known theoretical particle physicists in the world. Especially important were his contribution already in his early career time on quark, gluon, plasma, and he's an old soccer player in the soccer game of fusion. Therefore, our program, which is the wedding of nanotechnology with fusion, seems to be an optimal possibility for someone like Jan in fusion, to us who drive nanotechnology in the form of plasmonics in several places in Hungary. Jan is going to give his inauguration speech now, and the title of his speech is Modern Paths to Nuclear Fusion Energy, Elementary Particles, Lasers, and Nanostructures. Jan, please, the floor is yours.
Ladies and gentlemen, Norbert, thank you very much for this very kind reward or award and introduction. I'm very thankful and recognize the work and effort that went into electing me to be, which I accept very gladly, to be a foreign member of the Hungarian Academy of Sciences, MTA. Thank you very much, Norbert. Ladies and gentlemen, I have a pleasure of presenting this lecture to you on a topic which I would say is among the core of research which I have conducted over the last 50 years. This picture is taken in Budapest by László Csernai, who was just mentioned as another foreign member of the Academy. It is at the Liberty Square from a perspective which is not often seen, but it actually is Budapest scenery. And I added a small edge at the top because one of the friendships between, which goes very deep between nations, is the Hungarian-Polish friendship, and which goes with this proverb, Polak, Węgier, dwa bratanki, I do szabli, I do szklanki. Everybody knows what it means. So I do drink, but I don't have yet a saber. So maybe one day I will be also using a saber to demonstrate the friendship. The topic, as already mentioned, is very modern, and I will, however, make a great tour show it. This is the abstract you have all seen. This picture was taken a few days ago during a conference which was organized here in Budapest, the vacuum structure, particles and plasmas. And as you can see, I was already at that time lecturing, perhaps a little bit less formal dress to those present. And you see Norbert and Tamás in the picture. I will not read the abstract to you, but obviously it describes the content of the lectures. You will see it. So my fusion credentials, because everybody knows me from many aspects. Some people know me for strong fields, others know me for quark-gluon plasma, yet others know me for cosmology. So where did I get the fusion credentials? Well, they are actually hard-earned. First of all, I grew up in an institution which was very nuclear. I was trained and got my PhD very early at the age not yet 23, which means that all my peers today are already retired and gone. I am one remaining fossil in the game because I happen to be an American professor where retirement is not compulsory. And so this PhD was now almost 50 years ago, and actually this month I celebrate 50 years of published work. So it is actually 50 years since I became a scientist. And my specialty was theoretical nuclear physics. And even though at that time I moved very quickly into strong fields, my education is in theoretical nuclear physics. And then at some point when I was a postdoc at Argonne National Laboratory, a paper came into my hand about muon-catalyzed fusion. Oh, that's interesting, because I know how to do fusion and I know what muons are. Maybe I can do something about it. And then a couple of years later, when I already arrived at CERN, I wrote in 1979 on a paper on muon-catalyzed fusion, where several new ideas appear, which were very highly recognized at the time, and created a lot of activity. Some people were very excited about this prospect, and I will present it a little bit later. And of course, this generated a research program, as will be described, and then a few decades later, when lasers became powerful enough in terms of intensity, because power is one thing, but intensity and contrast is another, I was able to generate a research program in laser-induced fusion in Paris because of my personal connections to the strong field program in Paris, which was spearheaded by Gérard Mourou. And the person who was Christine Laboune, this group here is mostly female. I was with another student with the sole male presence in the group of research. I want to point out that Christine at some point remarked, she is a bit younger than me, but also right now retired, that there must be something wrong because all the women work with lasers on fusion. And, but it was not wrong. We did very good work, as you see, and there several papers came out of it, and a PhD of Claire Bacou, who is the second author on this particular publication. So I then, over the years, have been pushed and pulled by László, whom I see very often. László goes to many conferences I go to, and we overlap, and he always was telling me about his ideas in fusion, and I just listened. Oh, I have already done laser fusion. I have already, and then slowly it percolated to the surface of my brain that László was talking about something a little bit newer than new. And then when this program started, where Tamás Bíró and Norbert Kroó now direct, I was able to learn very quickly and participate in this program. So let me start the real lecture after this introduction with another introduction to fusion. And let me remind you that there are many different fusion reactors which surround us, both natural and planned man-made. It's not that fusion was invented yesterday. It was actually invented at the birth of the universe. Because in the beginning, there was Big Bang nucleosynthesis, the burning of elements. I will come to it in a moment. Or light elements were created. And then, of course, our sun provides most of the power. I say most, not all, because, of course, radioactive decay in the core of the Earth provides some amount, small percentage of power which warms the Earth. And but we are right now duplicating the idea of natural reactor. And one should really ask if that is necessary. You see, when you hear about nuclear fusion, we change the method of confinement, which is gravity in case of a star, and we use magnetic fields. And we change a little bit the fuel because we don't have time to wait 4.6 billion years. So we actually change from proton-proton reactions to DT reactions, which go much faster. But other than that, we are following the evolution of the chariots from 5,000 years ago, the standard of Wool at the top of the picture, through a droshka to the royal carriage. But the last red step has not been taken. The last red step is to really change completely the ideas which govern how we approach fusion, where we actually use new technologies which were not existent in nature at all, and a new approach to amplification of energy, which is also, although discovered randomly in the past, has not been used for any energy-producing processes as yet. Let me also remind you that the time scale and volume scale of the natural reactors is vastly different in different environments. If you look at the cycle of BBN, there were a few minutes' time to do the Big Bang nucleosynthesis, but the system was infinitely large. All universe was filled with a fuel which was actually doing the work. If you look at stars, we have a big fraction of the lifespan of the universe, but it is actually a very much smaller system confined by local gravity. And if you look at the gold carriages of our current effort, which are ITER, Megajoule, and NIF, I come to them in a moment, these are giants in the middle, both in terms of minutes or hours that we want them to burn, and in terms of size, which is literally, for this equipment, kilometer-sized. We're building gigantic equipment. And then the topic of today's lecture is this green bottom circle, which unites the more inventive approaches, which are muon-catalyzed fusion, proton-boron fusion, and plasmonics. And I will talk about these three after I introduce the others in more detail. So first let me explain why we need to do something new, because it is very rarely said. And I consider current efforts of the golden carriages of ITER, for example, as a no-go situation, completely a waste of resources, which could be used for fusion in a different way. And the reason I will explain in two steps. The first, you notice that I have two lines in each of these diagrams. One is called Bremsstrahlung, and the other is called fusion yield. And you can only have in a small volume a burn, nuclear burn, if the yield from fusion exceeds natural losses from Bremsstrahlung, which is the process of electron collision with heavy nuclei. And in DT, at least, you have a small range of 10 to 100 kV temperature where this could work as a thermal source of energy, equilibrium thermal source of energy. But the problem is a different one. The DT, which I describe in a second in more detail, you see above what deuterium and tritium are. They have the two heavy elements of hydrogen, produces in the process of fusion a very high energy neutron. This is the problem which is different from the question if it can burn. So one common solution of this problem in thermal environment is to go to proton-boron fusion. And I explained this in the other diagram to right, which is perfectly fine. We can have an energy yield, but the energy yield, a thermal energy yield, even if you could reach the temperature of 300, 400 kV, which is a unit which I will also define in a short while, is always below the Bremsstrahlung losses. Consequently, a thermal proton-boron machine is condemned to oblivion. It has to be a transient, non-equilibrium system, and that's what's written in all our publications. We started the modern era of proton-boron fusion, And in every single paper, 10 times, you find non-equilibrium, non-equilibrium, non-equilibrium. It's a very important element. So what is condemning the DT fusion? You see, we all have heard about alpha, beta, gamma radiation. And to stop alphas, literally a paper sheet is sufficient. Because of the typical energies in MEV range, they are degraded in energy of the depth of a paper. To stop electrons and photons, somewhat more extensive, larger screening is necessary, but it's commonplace. You can build boxes of radioactive material which you can put into your pocket with a little box made of lead. Nothing, so it's very easy to screen. The problem of radiation are neutrons. And there are two types of neutrons. There are those which are born at relatively modest energy, and these are relatively easy in relative terms, so to speak, to screen. You, after all, know, everybody knows that there are ships with nuclear reactors on them, and the sailors come back healthy. So it is possible to build small devices, small on the size of a ship. The problem really becomes when you produce fast, ultra-fast neutrons, which are particles which are in the DT fusion acquire energy of 14 MeV. That corresponds to velocity of 17.3% of velocity of light. That is actually a lot of energy in relative terms and requires many collisions to get rid of. And various strategies have been developed how to do it. And the question, of course, is how long before the reactor where these neutrons are produced en masse collapses, literally. And this is an unsolved problem. And anybody who says that we can run in a stable thermal environment, a reactor based on DT fusion, has to have a wake-up call, as I will in a moment show. So here's what happened. Physics Today, 1st of May issue, points out that ITER, which is the International Thermonuclear Experimental Reactor, shown on the picture in upper right, is in trouble because of British designed it, filled with 50 tons of beryllium, if I remember, and French workers don't want to work with 50 tons of beryllium. No, we're not speaking of a tenth of a gram. We're talking 50 tons. That's part of a program to harness the fast neutrons and breed more tritium in the process. And the article is very realistic, and I recommend to anyone who is proponent of ITER to read it quickly, because it basically says lots of problems are being faced. On the other hand, ITER got sponsored article in the CNN, so the gold coach of fusion research is a little bit in trouble. And we will see where it heads. You see the building is very large, which already is being mitigated politically. You see, America cannot afford a fiasco in fusion research called ITER without showing we already have another program. So they have called in on April 19th for a meeting at White House on modern approaches to fusion. And you can read it, you just type in the readout of the White House summit, and you will see that there were lots of interesting people talking real business. And this is prompted in part by the article in Nature, which you see below, which was on 18th of November 2021, which actually presented the 30 or so odd companies which approach fusion from a different perspective, which is our perspective. There are many companies. On the 100 billion end, which you see here in this diagram, you see ITER, NIF, laser megajoule, which is the French equivalent of NIF, National Ignition Facilities, the super whooper laser size, I mean kilometer size lasers. And then you go into some more innovative $100 million projects, which are, for example, Sandia National Laboratories with Z-Pinch. And then you have all these startups which actually collected $2 billion in private and public funding recently, of which the plasmonics probably counts in with $500,000 or $250,000 or whatever it is. Tiny amount, but it's also in Hungary, as you see. And these projects are explicitly committed to create non-equilibrium proton-boron fusion, like HP11 or Marvel fusion. They do understand the non-equilibrium aspect, which is very important. So before turning to scientific part of this lecture, let me bring back to your attention an event which occurred in 1989, which is called cold fusion. And you should remember that when something so fantastic comes close to being reality, which as it was already at that time, that there will be always people who will say, I have discovered fusion. This is almost unavoidable human element. There will be, if the project in Hungary is successful, I guarantee there will be people like that. So beware, this is stuff for movies. I recommend Doctor Who or this wonderful movie Saint, which I always enjoy watching again. This is very nice. It's all about cold fusion, but of course it's a fantasy for the movies, not for scientists. But you know, if you look for it, a few years ago, this was revived again. Airbus is filing patent for cold fusion. Google revives cold fusion experiments. You have to look at it and see what's going on. So the point is, it's very hard to disprove something. In science, I had a friend in coagulum plasma. His name was Emanuel Kwarczyk, and said, when you have a wrong experiment, you don't disprove it. You make a new experiment, which is right. Because it's extremely difficult to find what is wrong in the experiment, but very easy to approach the same problem with a different tool. And I think this is something to always keep in mind. It's very hard to figure out somebody's experimental result, which is you cannot repeat. How can he or she have a result I cannot repeat? A very difficult question. But it's, you have done your experiment, so you know that it doesn't work. So part 2. I have borrowed this title from a book which I highly recommend. For anybody who wants to know more about natural fusion, that certainly is in every aspect the book to obtain and read. Cauldrons in the Cosmos, Nuclear Astrophysics. I doesn't want to advance. Here we go. So a fusion reactor is powering our solar system. The sun is accretion of hydrogen and helium, some metals. Metals is anything which is more heavy than helium. And I know this is very funny, but this is what people use as language. And there are two sources of power in a typical star. There's something called proton-proton chain and something called CNO cycle. The CNO cycle will be both, I will both introduce both in a moment, but I want to remind you that it was for a long time believed that the CNO cycle is powering our sun, but when the models of the sun were finally came off ground, we're defining very precisely the pressure and temperature inside our sun, it turned out that the dominant cycle is proton-proton cycle. Most important, of course, for our existence is that the sun is burning in a stable fashion. At least over historical times, we know that the power output of the sun is constant. And if there are variations, they are related to the cold spot of the sun, which are called the dark spots. So there is some cycle, but it's not very pronounced. So we know that we have this PP powering the sun, and here's a brief, absolutely brief explanation. Right and left, you have two hydrogens fusing together under the pressure and temperature environment of the sun. There's a weak interaction process which releases an electron and actually a positron and a neutrino, and following which the deuteron fuses again. So this H2, as I explained in the prior transparency, fuses again with hydrogen, now via electromagnetic process, emitting photons, making helium-3. And then two helium-3s undergo a mutual reaction, producing alpha and two hydrogens. So in the end, there were two weak interaction processes, two electromagnetic processes, and one strong interaction process, which all add up to creating an alpha particle and recycling two protons. That's the PP cycle. The detail looks more complicated. This is now an explanation which says that aside of what I just described, which is on the left-hand side, with a small probability, given the pressure and temperature environment of the sun, we also can have a slightly variant that we capture the proton, and electron. It's a free body process. The proton come together, capture an electron, and what you produce again, deuteron plus a neutrino. Again, weak interaction process. But it's a free body reaction. So if the sun would be denser, that would go much faster, and that in part explains why there's a lot of variance for even in this PP chain, how massive the star is, and so that determines the lifespan of the star, what temperature it has inside, what density it has inside. So it's very, very dependent on the detail of a model, and therefore that's why. And you see when it goes on, I have explained most of the reactions. If you go to the side, you see the helium-3 goes to alpha reaction on the side. But there are all kinds of processes which can occur. You see 15% is helium-3 with already created alpha particle producing beryllium-7, and so on. So there's all kinds of processes which are occurring in the sun because there's no nuclear reaction which occurs with 100% probability. It's always environment dependent. You have a sequence of many reactions, and if you create an environment, part of the problem in understanding what is happening is understanding all the branchings which can occur. That's why, because nuclear reactions have branching ratios. So that's if we are successful in the plasmonic program, that will be the next step to understand precisely under what conditions what happens. The CNO cycle, which was originally believed to be the source of the power in the sun, is a catalytic cycle. It's a series of captures of protons, and which you see you can start with carbon-12, the most bound of the basis, so to speak, of our energy measurement in atomic physics. And you can do now, add a proton, emit a photon, you make nitrogen-13. Then you have a decay going to carbon-13. You now capture another proton and emit a photon. You make nitrogen-14, another proton emitting a photon. You make oxygen-15. Another decay, oxygen-15 is again radioactive, making nitrogen-15, and add a proton, and you strip the other nucleons, and now you have produced helium-4. So by sequence of 4 captures and 2 radioactive decays, in this catalytic cycle, you're creating the burn, which powers the sun, according to beta. But when the models finally were finalized, it turned out that only 1.7% is CNO cycle, and 98.3% is actually PP chain. So this just shows that you don't know until you know. This is just an ultra-short introduction to Big Bang nucleosynthesis. So what you see here is a classic computation, which I took from Petrou's recent work, Physics Reports 2018. And what you see is what happens when the universe burns. At 100 seconds, the real burn begins, and is finished at 300 seconds. So from 1.5 minutes to 5 minutes, a few minutes, boom. Once in a lifespan of the universe, a burn and then the outcome is all kinds of element abundances, which all disagree with what we see in the outcome. And this is really one of the problems which, one of the research topics which I am interested in on the foundation level. If you want to do research in nuclear fusion, one of them is to improve understanding of the BBN processes. And you know, if you want to know how much money goes into it, somebody just built a whole laboratory for radioactive beams for $1 billion in America. And almost every nuclear laboratory, including CERN, has radioactive beam facility where people look at these reactions as a function of time, because many of these reactions involve isotopes which live for milliseconds or seconds. So you cannot accumulate them and then try out. You must actually do the experiments while the work is in progress. So if, basically speaking, we don't understand at all the burn in the BBN for anything but hydrogen, deuteron, helium-3, helium-4. Everything, lithium-6 is in doubt. Some people believe it's okay, some people believe it's not. Lithium-7 is way too low, and so are all the other elements. And you see here the chain of reactions, how complicated it is to actually understand the burn which occurs in the Big Bang. It's actually more complicated than the burn in the star. The problem of a star is to understand pressure and temperature in the center where the reactor burns, because it's a self-consistent problem, because the radiation emitted in the fusion keeps the star from collapsing. So it's a dynamic, you have more yield, then it goes apart, but if you have more mass, then gravity pushes it together. Okay? BBN is a different mathematical problem. So outcome of all this, so outcome of the cauldrons in the cosmos is a distribution of the abundance of elements, which we measure. The two effects are here combined. One is the binding energy of nuclei, which usually you see people like to show the fact that iron and nickel are the most bound elements, and then other elements are less bound, so everything ultimately becomes iron, nickel. Obviously not everything, because we have all the elements in some abundance. And it's very easy to see the anomalies. First of all, you see the zigzag up and down. That has to do with the spin pairing and proton-neutron pairing. You win almost always when there's even number of protons and neutrons. That's why you have more abundance of this and less abundance of that. And sometimes isotopes come, a long list of isotopes, so you're mixing the abundances, and that's why it's not so pronounced up and down, but a little bit average. Then you see at the bottom left the light elements, lithium, beryllium, boron. These are the elements you should remember, because they will be the elements we will study in plasmonic fusion. They are at low abundance, but it's not very low. Look, all heavy metals are at this, less abundant. You know, uranium, if you look here at the corner, is much less abundant than any of these. So it's low, but it's not something which is rare. And so these are they are very little abundant, because they are hard to make a nuclear burn, and in fact, they can be easily depleted. And therefore, what is, the literature will tell you of these are so-called spallation products, which may or may not be true. I don't subscribe to this. I'm just reporting. And spallation is that you, for example, to make boron, you hit carbon with a fast particle in an atmosphere, and it strips away another proton. That's called spallation, and then you converted a carbon-12 into boron-11. That's a very standard reaction, and we know all the cross-sections. You know the cosmic flux. You can compute the rate of production of boron in the atmosphere. So this is something which is the belief, but it doesn't work really well. So that's a problem, which is we do not understand the abundance of elements which are of interest to us, and that's always a bad sign. Something can be learned. And also, if you look at the thorium-uranium puzzle, it's very nice because it takes a moment to realize the very naive explanation of thorium-uranium abundance is that it was all produced early on in the universe, when the universe was a couple 100 million years old. That's a very unorthodox explanation, but I'm giving you my view. The lifespan of thorium happens to be, the half-life, exactly the lifespan of the universe, 13.5 billion years. And uranium-238 is 4.6 billion years. So you do the trivial back-of-envelope computation, you see that these elements were produced at equal abundance with bismuth and lead when the universe was young, when all these massive stars exploded right and left. And since that time, uranium is just decaying, very little more is produced, and we have abundance which we see today. So this is my personal view, but it is working very nicely. I need to move on. Yes, so we're coming to part 3. I was reminded that I don't have all the time, but just my time. And so this is the muon-catalyzed fusion. In the nutshell, Scientific American, year 1987. I write the Scientific American article with Stephen Jones, who ran the experimental program in Los Alamos, and we discussed how do we call it to get attention. And we decided to call it cold fusion, because you can run it at room temperature. Nobody forces on you any new temperature. It's 1987, notice please. Okay? And I wrote into this can mu by hand, just to make sure you understand this is not a cold fusion. Our name was hijacked from us by people who said we can do it better. Muon-catalyzed fusion. So muons are elementary particles of approximately 200 times the mass of electron, the heavy electron. When you have a heavy particle, a system is smaller. A physical system is smaller. When a physical system is smaller, in hydrogen molecule, which is now muonic molecule, fusion, spontaneous fusion occurs on a time scale of picosecond. So in the ground state of dt mu molecule, fusion occurs at 1 picosecond scale. Boom, boom, boom. So all the problem we have, and muons live microsecond, 2 microseconds. You want to have million fusions per muon? All you need to do is to recreate the dt mu molecule fast enough. Cycle, catalytic cycle, but the catalytic cycle, unlike in the sun, CNO cycle, here the catalytic cycle has to run fast because we have only 2 microseconds. And muons are costly to produce. So if you want to have a muonic reactor, you have to manage the timescales in atomic physics. It turns out that this is molecular and atomic physics to incredible degree. I have never, although I grew up doing lots of molecular and atomic physics in my research, this was really testing my skills. A lot of very detailed work. And the problem of muon-catalyzed fusion is that some of the alphas which are produced in the fusion catalytic cycle steal the muon. Once the muon attaches to the ground state of alpha particle, and the alpha particle runs with the muon, it has only about 30–40% chance of being stripped again. So we lose the muon with certain probability, and so the limit of about 200 fusions is achieved. But you have to remember, what gave birth to the cold fusion was that we achieved scientific break-even in this research program within 3 years. This is unheard of and very little talked about 30 years later. But the problem was that we never, I should have, this we called cold fusion, when somebody else called his invention cold fusion, and we lost funding and lost support because we were cold fusion. We were not cold fusion. Let me just explain that there are many muon-catalyzed fusion reactions. First, in hydrogen, you have everything imaginable. You have PD, DD, PT, DDT, TT. Muon is always circling. That's what Tamas reminded me, that's one of the corrections I introduced into transparencies, that you don't make an arrow, you put mu in parentheses because muon is catalytic agent. And he reminded me that's what chemists do, and I followed his advice. So this is something to keep very much in memory, that we have many reactions. But you look at the next table, there are even more reactions. Look at this table. These are all reactions I can catalyze with muons involving light isotopes. There are also the reactions we can try with plasmonics. All of them. Something to keep in mind, the field is very, very rich. The reason that we didn't try it is by the time we were ready to try it, the funding for fusion with muons dried up because of a cold fusion mix-up. And all we need to do is to find resonant reactions, because you see, just let me give you a very, very small instruction in muon catalyzed fusion. T mu, which is here, the heaviest isotope of hydrogen will capture the muon ultimately, because it, by reduced mass effect, is most strongly bound. T mu looks like a neutron. It's not a neutron, but it's a neutral particle of small size. So it will very quickly look for something to attach to. And we want it to attach to another D molecule, electronic molecule, and it does so by binding, creating the DT mu molecule in a resonant condition with 0.4 eV. The electron molecule vibrates, and DT molecule is created in a relatively large size. That's how it works. Such a resonance in all these reactions. There's a resonance in DT mu. Why there should be no resonance in 50 other reactions which we can study? Let us move forward 20 years. Quark-gluon plasma is in between. We created experiments, analyzed them, discovered quark-gluon plasma. 20 years in my life. Okay? Back fusion, thanks to strong field component in my research, I discovered the Paris group, and we actually have a pattern. I just wanted something should be a headmark, a watermark of this research. We have patent which is called production of energy via laser-initiated aneutronic nuclear fusion reactions. And in the midst of this patent, several times non-equilibrium, here see, produce non-thermal equilibrium, aneutronic nuclear reactions. This is very important. Non-equilibrium. In the patent, everywhere, keep it always in mind, we are not working on thermal reaction processes. Direct, we call it direct reaction. You make reaction, boom, 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 boom. We work, our initial research was based upon the idea that we can blow away with a nanosecond laser electrons from a target, boron target, creating a plasma, charged plasma of boron, which we then irradiate with laser-generated, pico-laser-generated proton beam. And then all the rest of the picture is basically diagnostic to prove that we produce alpha particles, because alphas ultimately are the only convincing evidence of nuclear fusion. If you don't produce alphas, then you have to explain yourself to the community of nuclear physicists. And we've showed this in two different ways. By using a polymer detector, CR39, and by using a Thomson magnetic spectrometer, which you see here schematically at bottom left. And this experiment was successful. We beaten vastly the yields which were previously tried with one single laser shot by a Russian researcher called Bielayev, by orders of magnitude. And at some point, we were even shut down as an experiment, because as a side chain of this experiment, we produced radioactive carbon-11, which we patented then. You see, you're after nuclear fusion, but you produce other things. I explained to you the branching ratios. So we produce a lot of carbon-11, which has a lifespan of 15 minutes. Suddenly all radiation detectors went off, and I was still not awake because we had long night shift. I come to the lab. Oh, we have been shut down. So it does happen. Then we did that again. Now you see even a smaller team working on boron nitride. I don't want to go through the details. So boron nitride is now duplicated. So the last paper I found was from January 2022. So this is not something which stopped. People who, there's lots of activity. There are two companies which have $50 million each, or order of magnitude, in research funding. And you see, the BN is used in this here and there. And this is the blue signs are specific per unit of energy, yields of fusion, which you see here on the left-hand side. So normalized flux of energy and normalized flux of alpha particles per joule. And you notice that in our experiment, the yield increased by 2 orders of magnitude by replacing boron with boron nitride, which was my idea, which we patented as well. But this expired. You see, we only maintain, because of various political issues, we maintain only the laser patent because, you know, you have to make a strategy of what patent to keep and what patent to drop and so on. And so you see here lots of work which followed ours. So this is us. And you see we beaten the prior experiment by like 3 orders of magnitude and then beaten again by 2 orders of magnitude. And these were clones of our experiment, which were slightly improved. I don't even know they had more yield. Perhaps they had more measurement skill to find the alphas. This is also something to keep in mind. So you see, there is a lot of, and let me just add, to end this cycle of presentation, remind everybody, all this depends on having the proton beam. Proton beams can be, of course, purchased off shelf. You just open and buy an accelerator. It costs a lot of money. It's not very portable and sometimes requires a team of 20 people to run. So there's all the interest, especially in the medical profession, to miniaturize acceleration of particles, and that is where this work is. You see here title, this is a preprint, which I think is submitted to Nature the way it's written. Preprint on archive, you can find it, low divergence MEV class proton beam from kilohertz driven laser solid interactions. Okay, so there are people who only try to make good proton beams. And I have below a typical spectrum of protons. So from perspective of building a proton-boron transient reactor, I think the path is growing very rapidly. The approaches are very rapid. So now plasmonic fusion. We are, with proton-boron laser fusion, we really were trying to fly a plane, a space plane, but this is actually more of a space plane. Because now because it combines lasers with refinements in target technology. So that actually is, see, we did nothing about this. Our target was aluminum foil, standard issue, coated with oil, totally trivial, naturally occurring in any vacuum chamber. If you have and actually, as Laszlo pointed out, this is a mishap for this picture because it's not even the right vacuum chamber. Now, let me just say something which matters. The chambers in Paris, which we were using, were like 5 times the size. We could put inside what we wanted. Because the French have invested in their detector hall. They know that if you don't have space, experiments are hard to run. So their vacuum equipment is really vacuum equipment. some of the chambers are, you can put me in. Okay? Standing. And there are pictures like this of people. So I didn't want to show it. So it's really very important to recognize that the equipment matters very much. It's not only the laser, but how you actually can run an experiment. So plasmonics, I got a crash course from various friends. As I told you, Laszlo played a role, Norbert played a role, Tamas played a role, and you see here, I even learned that you don't trust Wikipedia. I always tell my students, never trust Wikipedia. But I wrote Chartres, not Chartres Cathedral, but Reims Cathedral. That's wrong, as pointed out of one of my students. When I gave a practice talk, Stefan, whom you know, Stefan Evans, who is fanatic about stained glass, told me, this is not Reims Cathedral. Reims Cathedral was bombed out during the Second World War. This is a picture of the only surviving Chartres Cathedral. So I went and checked, and he is right. So he knew. You see, when you go and have good students who are artistically inclined, you know such details. So the other thing is perhaps even more exciting, is the Lycurgus cup, which you see here, electron transmission microscopy picture of a 550 nanometer, not a rod, but a square inside the glass of a cup. They're using actually 50 nanometers, nanoparticles, to create the light phenomena, which you see now here in the picture on the right. This is stunning. So if you can change color at will. The Romans, and they made the nanoparticles in situ. It was not that they had a machine to cut gold into pieces. They added gold and silver and something else and waited nicely curing the glass, as this article, which is published in the journal Gold. I decided not to put this on the transparency, but it is published in journal Gold, and it's by Jan Freestone and Company, on all the things, all the diagnostics that has been done on this Lycurgus cup, which is nanotechnology in the action. So when I proceeded to look more closely, is that already used in today's technology? And if you type in nanotechnology, nanoparticles, the first thing you come across, two things: treatment for cancer and enhancement of solar cell efficiency. Obviously, why solar cell efficiency? Because you can use a bigger fraction of a spectrum. We now live on a very tiny fraction of a spectrum in all solar cells. 90%, 80% of light that hits a solar cell just heats the cell. So if we can actually shift the light more towards the useful wavelength, then we would have a much better efficiency. So that's solar cells. But this is actually much more interesting, the treatment of cancer. So can you ban cancer without cutting open the wound? And apparently the plan is to have gold nanoparticles, which obviously will be flowing through your blood system and attaching in the active domain of this illustration of a breast. And then you irradiate it from outside with a long-wave infrared beam, and they absorb, they are in resonance, the radiation, and kill the cancer cells they are attached to. A great plan. I think I have heard of it even before I became interested in nanofusion. Because number 3 is the NEPLIFE project, which has a base on a slightly more sophisticated use of plasmonics. Because if you study light interaction with surfaces of nanoparticles, you discover that the electromagnetic fields are, as shown here in the picture, they are actually far-reaching. As Norbert is telling me, 150 atomic layers, strong electromagnetic fields reaching out of the surface of a nanoparticle, which resonantly, that's not now, that part is absolutely certain because we see it of a Lycurgus cup. You absorb light resonantly. And the question is, what does it mean? Well, this picture is a numerical simulation. It shows that there's a huge electromagnetic field reaching deep into the surrounding material. If so, if you have been around particle acceleration with lasers, this is doing the job much better, because electrical fields can accelerate particles collectively. And therefore, the hope is that we concentrate laser light by this factor 1,000, at least someplace here I put the number 1,000 of the transparency, oh yes, at the very top, because that's what numerical codes say. Norbert told me, no, don't believe 1,000, 100 perhaps. But I believe, because I'm a theorist, numerical codes. So then, this is now an UDMA polymer, which in this particular situation is a carrier of a nanoparticle. Just like glass was carrier of a gold nanoparticle in the Lycurgus-Cap, the team of Attila, who is here, and Norbert and Tamás came up with this particular polymer, which is UDMA, as a carrier of UDMA mixed with something else. I will certainly be beyond my knowledge of polymers when I start figuring out the more complicated name. But the point of this matter is that it is also a detector. You remember you actually brought Cr39 extra into the chamber, reaction chamber, because it's a natural, any polymer is a natural detector for alpha particles. Alpha particles damage the polymer. Cr39 is this. My glasses are made of Cr39. And UDMA, someplace I have a crown, is made of UDMA. So yes, I am full of polymers. And so is probably anybody who is a little bit older as well. And so we have to remember, right now, UDMA is a carrier of nanoparticles which are going to catalyze the nuclear reaction at the same time as it can serve to be a detector. In future, we can actually, perhaps, change the role of UDMA, of the polymer, to be part of the active system as a fuel. But that's something which needs to further work. All I need to say is that the gold particles, nanoparticles, will be tuned to the available laser wavelength, which is here 795 nanometers, and we run experiments. And then I have a policy of not talking about unpublished work beyond qualitative, what's already in the open results. So I will not discuss any results of NAP live plasmonic fusion, other than to show what is in many pictures shared with funding agencies, shared at conferences. It shows to you what happens when you shoot at an UDMA target. On the right, no nanorods, no gold nanorods. On the left, you have nanorods. And you see a greater volume, greater irregularity, something new is happening. There's no question about the fact that a much more violent reaction is catalyzed by a combination of nano antennas with the carrier UDMA. And if one looks deeper, there's a suggestion in this picture that maybe alpha particles were present, which are drilling holes in front of our eyes. It's certainly different morphology, which requires much more analysis. But you see, this is a detector for exactly along this. We did exactly the same thing with proton-boron fusion, except that we put the Cr39 into the chamber, took it out, and then after some treatment looked at it through a microscope. Exactly the same thing. It's an active detector right there in front of our eyes. We need to learn how to use it. There are various methods how can it be done. Just think of it that we did this in our case. We took our Cr39 and took to another lab and put it in front of alpha emitters, just to see each energy of the alpha, what damage it does for the, after we treat, because you see, we treat this target. It's not that it's looked at, you take it out and look at it. It is actually processed in various forms, and you have to see what happens when you actually put it into well-defined alpha beam, process it, and then look under the microscope. And that is what we did in order to be able to say, tell the world, and everybody since that time, when we did it 10 years ago, repeats our experiment actually exactly. And we publish the methods in Nuclear Instruments and Methods. I didn't show it, but we have 1 or 2 papers on what we did in there. So because a method has to be established. You cannot just say, oh, we did it. So let me conclude this lecture, which probably I didn't watch my time, but I'm sure it's over time. Reminding you that 5,000 years ago, and standard of wool shows you wonderful horses pulling wonderful carriages with wonderful wheels, and the source of energy is hay. And our objective, reminding you, is to build a space plane where the atom is the source of energy. Totally different strategy and totally different approach to the question of energy production. It's clear that plasmonic fusion satisfies all the criteria, which I would put to a realizable fusion approach. It's compact, aneutronic, lots of different nuclear fuels can be attempted. I wrote here different, but lots of different nuclear fuels. We can explore the processes as we do now with commercial laser technology, but it's certainly scalable to much more powerful lasers as needed. Needed for either amount of power, or needed because we want, for particular reactions, to create small micro-explosions. Whichever it is, we will find out, because it's a very rich research program which is not finished in 3 days, or 3 weeks, or 3 months. So to finish, I would like to thank several people. This is always customary to do that, and I think it's really important that it is actually said, not only shown. There was a man in my life who really wanted me to do fusion. Even before Norbert, there was Ryszard Gajewski. He's a Polish plasma physicist who really believed that ingenuity is sufficient to solve the fusion problem, and he was a really good friend. Steve Jones, for his very happy years of collaboration in ion-catalyzed fusion, and Christine Laboon for her absolutely superb leadership and dedication to laser-driven non-equilibrium proton-boron fusion. That's quite a remarkable person. Then there's Tamás Bíró, Norbert Kroó, and Peter Levay, who are my hosts here in Budapest. And there's László Czernay, who is not here today because he has a very important other meeting. But I must say that I wouldn't be standing here for sure if it wouldn't be the friendship with László. So I tell you now a small anecdote. We were at this wonderful party after the Balaton meeting, and Victoria fell sick because he had at the time, you know, the gluten intolerable. László just took us home. Okay? And while we were driving, he non-stop was talking about nanofusion, plasmonic fusion. So maybe by being very kind, he did bring me to the attention of Norbert and reminded you that I am around. So his kindness was certainly important. Andrew Steinmetz is a graduate student in Arizona who is virtuoso in doing things with PowerPoint. I could have created this lecture in approximately 500 hours of work. For him, it's 5 hours of work. I mean, it goes like, I don't know where his skill comes from, but he's fantastic. Quite aside of being a fantastic physicist, he's really good and willing to help. Just like László helped us driving us home, Andrew is always there when I need help. Thank you all. I hope you enjoyed this tour de force. Thank you very much.
Thank you very much, Jan, for this very interesting talk. The tradition of our academy is that after inauguration speeches, we don't open time for questions. But I would like to mention something else. Of course, there are some conditions for being elected as honorary member with all the rights of these members have. The first one is outstanding science. You did it. The second one is to have some relation with science in the country, first of all, in connection with the Academy of Sciences. The third one is that you should accept the invitation. The Hungarian Academy is honored that you did so. And finally, the last one is that you have to give your inauguration talk. You did it. So with that, you are not an elected member, foreign member of the Academy of Sciences, but a member with full rights and duties. And in order to document it, let me hand you over the diploma on that. My proposal is that you should open it. And maybe show it for the photographer.
Can you help me, Norbert?
Yeah. Together with the label, which is a stamp of the Hungarian Academy of Sciences.
Maybe another picture.
And by that the meeting has come to the end. Thank you very much for your participation. I hope you enjoyed the talk as well as I did. Thank you very much.